what are the goals for today? So the goals going to be that I give you another proof of the Weekend Theorem. That's the first goal. The second one would be, like from the theorem, what we proved that we're gonna obtain, like the calibrated curves or backward characteristic. Gamma mapping from minus infinity to 0 to the torus, with endpoint to be any given point, any x given in the torus. Okay, so that's our goal. So I would say that the proof I'm presenting today, the first proof was by using instability and by using like there was a Lipschitz function being dominated by L plus C naught, and then we take the limit to infinity and we take instability to get the deduction. So today's proof is really different. So the second proof for today is really by a fixed point theorem by using the Schauder okay. And I think that this was done by Fateh. I think I'm not 100% sure. And this outlines a a main principle in analysis, also in PDE or dynamical system. In this aspect is that if you have a priori estimates, if you have something sort of like better, so you start with something and you have something better, then it's typically a compactness result, in which case you have your operator is going to be compact. And once you have compactness, such a compactness result, you can, compactness again corresponds to the smoothing effect. So I would say that smoothing. So the general principle is that smoothing effects corresponds to a compactness result, right? Because you start with something rough. After you run the operator, the PD and stuff like that, you end up with something better. So that's sort of like a smoothing effect or a compactness result. And then from this compactness result, you can use using a fixed point theorem to get existent result. So that's sort of a general outline, general principle for proving existence of solutions to certain operators or certain PDEs is always going in this sort of same manner. All right. Not always for other kinds of PD that you don't have smoothing effects, but for the ones that you have smoothings, and how it goes. All right, so let's do it. The key point was already established the other days, right? You fix a time sigma, then there's constant C sigma greater than 0, so that this whole operator, even you map just from the space of continuous functions, but it's going to be equi-Lipschitz in the on here with the Lipschitz constant less than C sigma. So it's smoothing effects if you go from time sigma to infinity, right? So we start with just the space of continuous functions. So after time t greater than equals to sigma, you have this whole family t. Let me omit the minus size. Is equilicious on t and cross sigma infinity, okay, with the constant c sigma. So that's already a smoothing effect, right? Because you always start with continuous function, but your operator allows you to get equilicious on the whole space. Um, Now, this is not yet what we want. There is another issue that that in order to have compactness, you not just need that your set of functions is equilicious, but you also need that it to be bounded, right? So that's something that we sometimes might forget to use certain compactness result. In our case, we are using acyl ascoli. Not only that we need it to be equicontinuous, but or equilicious. But we also need that the set of functions is bounded, and that's a technicality uh, that is not yet bounded, right? So I would say that, but this is not yet bounded in whatever in C of t n cross sigma infinity, for example. Why is it not yet bounded? You can think that it's clear, right? If you add a constant, like it's already clear that we have tt of u plus c equals to c plus tt of u, right? So if you keep adding constant, then you know then the result gonna be anything from minus infinity to infinity, right? So that's not controlled. Therefore, in order to have compactness, for sure that we need to fix this issue. And in this case, we're gonna essentially mod out the additive constant. So that's a natural technique that if you have something sort of like shifting around, and you can mod it out by essentially considering the new space E is just the space of continuous function mod out uh, just additive constant, right? So it means that we put phi and phi plus c to be in the same equivalent class, and we write uh, so we write the equivalent class phi to be phi plus any additive constant. So this is again a very beautiful technique. Just something, and then you can define a new norm in this space E to be the infimum over all choices or possible constant. And actually you can draw a geometric picture of this phi, the norm of this equivalent class phi in E, right? Can be seen geometrically as following. Okay, so if this were space, this was phi, you have a function say phi like this. Okay, so if it's all positive like this, right, um, then if you take the L infinity norm, is going to be big. So the rho of putting in the the constant is that it allows us to shift things around. What? Want to place it to get different copies. So you can shift it around, and once you are shifting it around, it seems that if you shift it to the correct one, that um, it's changing around zero, then that's the best case scenario, right? And that's the shifting constant that allows you to minimize the norm in A. So this is what? So this is phi plus c, and you're just taking infimum over all c of phi plus c in L infinity. That's it. And it's clear to us that the infimum or minimum happens when phi plus c, uh, you know, you know, how, when phi plus c is changing sign, right? Switching between minus and plus, then it's the case in which that the norm is the smallest. Okay. Um, and because of exactly that what we said earlier, right? If you take the semi group, apply on u plus c, then it's the c can be pulled out as tt of u plus c. Therefore, you can think of your semi group as just a mapping from E to E, right? So that means that you mod out all possible additive constant, right? Um, so, again, you can see that tt uh, of phi is just gonna be in A, right? For any equivalent class phi in A. All right, and this is good. This is good as we manage to avoid the unboundedness issue. Okay? That's the key thing, right? Because remember that earlier we said that because you can add any additive constant and secant goes to infinity, minus infinity. Therefore, although the map of TT acting on continuous functions is equiliptious but not yet bounded. But once we mod out the additive constant, is automatically bounded. Why is it so? Well, it is so because if you fix sigma greater than 0, right? So you have we have uh, T sigma of ux minus T sigma of uy is less than equal to C sigma of x minus y, right? For any xy and for any u that is in the torus, space of continuous function in the torus. So you see that it's really beautiful that it's already Lipschitz, right? I just recall what I wrote down there. And now because of the fact that we mod out things, you can also see clearly that, T sigma of an equivalent class U in L infinity, this one is always less than equals to, whatever. You can just choose C so that T sigma having the mean value is 0, right? Then T sigma in L infinity is just going to be less than equal to C sigma as time root of n. If we take C so that what? So that's mean of uh, mean of T sigma of U plus C, mean of x in that equals to mean of x of T sigma of ux plus c equals 0. So you just pick a random c so that it has the mean as 0 and then equals to 0. And because it's Lipschitz in the compact torus with the diameter at most root of n, therefore we obtain furthermore that, again, this is bounded. Okay. So we have shown that the map T sigma is equiliptious, is bounded. Oh my God, this is not good. What scalar is that? Okay, let me just write on the right panel then. I'm sorry. So I have T sigma mapping from E to E is compact, right? So that's a compact map. You see, that's exactly the point from smoothing effects, right? We have T sigma mapping on E is bounded, and by Azela Ascoli is compact. So by Azela Ascoli, right? So it's compact, and then now we can quote the Schroeder theorem. Schroeder theorem, it's in all kind of PD textbook, or you can just search on Wikipedia if you haven't seen the Shadow theorem. You know, E is just need to be a convex whatever subset of a vector or a norm space, you know. And if T is a map that maps the set to itself and is compact, then you can find a fixed point. So you can find U sigma, an equivalent class in E, so that T sigma maps U sigma to exactly U sigma. So that's a fixed point theorem. And clearly that if you repeat the semigroup, you apply the semigroup multiple amount of times, and you have that still, you know, dk sigma is still of U sigma is still sigma, right? So there exists U sigma such that the sigma of the equivalent class U sigma equals to U sigma. And this also implies that you repeat it k times, is still the same. And now we are gonna use the normal trick in you know, from here I need to deduce that this correct not just for k sigma, but it has to be correct for all for all possible time, right? And this is a normal trick in analysis that we're gonna, you know, do it for you know, so from here to have k sigma correct, to have this one correct for all time, I'm gonna use the trick that, you know, big sigma is 2 to the minus j, and then let j goes to infinity, right? Because, you know, again, we need to start with some positive time, and any 2 to the minus j is fine. It's a positive time. You have a fixed point and you let j go to infinity, you can approach 0, and then by approximations and smoothing effects and continuity, you have that you know, for each of the j you have a fixed point, and this is correct for any k times 2 to the minus j, and as j goes to infinity, k times 2 to the minus j is approaching any positive constant as you wish, right? And for j goes to infinity, again, you can assume that uj converging to u for some u. Again, this you can check me. Um, um, Again, you know, that's not complicated. And then by continuity of the map, you can deduce that u is a fixed point of this semigroup. So tt of u is always equals to u for all time, right? So that's exactly you know, again, it's beautiful, and it's essentially how to put it, it's essentially an interesting point there. Okay. One of the interesting thing here is that you might wonder, how do you know that uj is equi-Lipschitz to goes to you know, to use Ascoli theorem to pass the limit, right? So how do you know this red box I'm putting on the left panel? But remember that if uj is a fixed point, okay, maybe just quick, yeah. So note that if you have t of 2 to the minus j uj equals to uj, then this also implies that t1 of uj equals to uj, right? And because of the time is 1, this helps us to imply that uj is Lipschitz with constant c1. Okay, that's why we can pass the limit. This is beautiful, you know, the idea is really beautiful. We really need uj to be equi-Lipschitz to pass the limit, right? Okay, yeah. Anyway, again, just a simple trick in analysis, but all in all, it's really beautiful and amazing. Okay, now we are almost done. We have this semigroup that holds for any time t, positive or non-negative, right? Still, we are not yet done. because I need to get rid of the equivalent class now, right? So thus so far we have uh, there exists u in CTN such that, in fact, u has to be Lipschitz here, but tt of u equals to u for all time greater than 0, right? So we now need to get rid of the equivalent class. And this is interesting. This is sort of like additive result, and also it's sort of like, I don't know, um, this can be a result for people studying analysis or some interesting problems for kids who are interested in, you know, uh, functional aspects of things, right? We see that because of TTU equals to U, you know, you can just write this one as, if you get rid of the semigroup, this just means that you have TT of U equals to U plus some constant CT, for some CT being a real number. And of course, you see that CT has to be continuous here, right? So T maps to CT is continuous because the semigroup is continuous and is additive. Because you see that T of T plus S of U equals to U plus CT plus S, but this one is also equals to TT of TS of U, and this equals to TT of U plus CS equals to U plus CS plus CT, right? So therefore you get that CT plus S equals to CT plus CS. So it's an additive function, additive process. Therefore you can just write it as, you know, it's additive. So you can obtain that CT is just a linear function, right? So it's minus C times T for some constant C. You're gonna put the minus there, minus C there, so that it just add up and correct the correct sign for the conclusion. So we thus conclude that we've thus conclude the result, and this is a semi-group result. And we have so far that there exists a function u, a fixed point of this problem. And again, I would like to share with you this principle, because not just here, but also in lots of PD problem, you know, not just with me, my students, and all the other issues that I have encountered, that many times proving existent result is not too hard if you have a priori estimates. If you have smoothing effects, and if you phrase the problem correctly, then you can prove that there exists such a function u. And many times that you can interpret your problem as a fixed point problem. Again, I don't mean that it's easy, but it's sort of a procedure that you can go in this manner. Again, after kind of well-posedness result, we would need to go really deep in going further to understand more of the properties, deeper properties of the solutions, and that's much harder. That's a next level, a different issue, but I mean the starting point was that. Let me pause here now for any questions or concerns. Any point that you would like to discuss with me up to this point? Okay. Right. So now let me end um, class today. Not end, but I mean end the content of the class by presenting the second part. That once we have this u here, once we have this one here, or maybe it's also this one here. Once you have that is satisfying this semi-group property, then you can utilize this semi-group property to so this one gonna implies the existence of calibrated curves. And by the way, this is not easy. As I said, we need to have enough regularity. We need to have enough convexity and stuff like that. And in practice, there are a lot of counterexamples and a lot of delicate issues that even if you have a fixed point result for the semi-group in the PD language, that's fine. But to go from there to the existence of calibrated curves and deeper properties, we would need to have much more assumptions, which is exactly in the light of what we have here. And I'm sure that if we are not having enough of the assumptions, then things might go wrong, and you know, and one has to be really careful in various problems in research if we are losing certain like certain assumptions or certain smoothness or certain convexity. um, and as I said, uh, I am aware of some counterexamples in which that you have this property, but you don't have, the calibrated curves, or the calibrated curves don't satisfy the Euler-Lagrange equation. Okay, so now we're gonna construct the calibrated curves in an iterative way. We're gonna end with the point 0, and we are gonna construct it this way. And in fact, there are many ways to do it here. This is my favorite way, and I think that it's to me is kind of a most natural way. This is also the way I wrote down in my book. You can check the parts about backward characteristics in the chapter 5 or 6, something like that. It's done in the same manner. What we are doing is that you start with the point X, okay, and you're trying to construct the calibrated curves, uh, okay, so let me write down. So to construct the calibrated curves, gamma going from -infinity to 0 to the torus with gamma 0 equals to X. I'm not in a hurry to construct it directly from -infinity to 0, but we're gonna do it iteratively. Like gamma, first make it just from -1 to 0 to the torus, and then -2 to -1 to the torus, and overall you can construct it from iteratively from -k plus 1 to -k to the torus. Okay, and that's sort of the way that we are doing it, and you can see it here. First, I'm just using that, again, I'm just using the term 1, right? So I'm writing down is that I have u equals to T1 of u plus C naught, right? Just use it for term 1. Okay. And for term 1, you fix the point X, right? You fix X to be gamma 0, then you can find, let me just write down, and then I'll explain if there's a need. You can find your minimizer gamma, so that this is the case, right? So you have u minus X is equals to the action functional here, and we have the minimizer because of the first 10 lectures we developed that there's a minimizer, plus the endpoint, which is u of gamma minus 1, right? So maybe let me explain the whole thing, and let me just write out this step. Why do I have this step? Again, it's clear from what we have done, but I'll explain it again in case there's a confusion. So we start with X. We have ended up with the new point here, which is gamma of -1, right? And now you do it iteratively from gamma of -1, you do it once more. You know, one more step, you end up with from gamma -1, you get gamma -2, and then you can just do it iteratively to get everything. And that's exactly the point. You go from u gamma of -1, you have the fixed point property for time 1 as well. So you find another curve, calibrated curve, so that you have this property, and it's equals to the action plus the endpoint. And keep repeating this. You have constructed the calibrated curve from -infinity to 0. Okay. So maybe let me mention 2 points and then I'm done. So 2 points, right? The first one is just a clearer explanation of why can I find gamma going for each of the unit time interval. So I have ux equals to, let me omit all the minuses here, right? So t1 of u x plus the constant c naught, right? And I recall what is this one, right? t1 of ux is the mean of y in the torus of the action functional. So h1 going from y to x plus the initial value is uy plus c0, right? And we have discussed about this, right? Both of the things inside the bracket are continuous. In fact, they are Lipschitz. So the mean occurs at some value. There exists a z, so that is equals to h1 of zx plus uz plus c naught for some z in the torus. Okay. And you know, again, this one has a minimizer, so there exists a curve gamma, so that and I'm going to shift the time. So this equals to integral from 0 to 1 h not h l of no, let me shift the time right away. I just, you know, it's just a integral in the unit time interval. So I'm just shifting the time from -1 to 0, gamma s, gamma dot s plus u of z plus c naught for some gamma, which is in ck, right? We have proved the regularity results, -1 0 with gamma -1 equals to z, gamma 0 equals to x, and that's it. You can just repeat the result. That's the first point I want to mention. The second point I want to mention is that by our construction, we have that gamma is in ck of any interval, like from -j plus 1 to j, for any to -j, j greater or equals to 0, right? But in fact, we have that gamma is in ck for the whole interval from -infinity to 0, and gamma satisfy the Euler-Lagrange equation. Okay. Why is it so? Well, you know, although that we have only constructed our curve, you know, going in each of the unit time interval, right? But remember that it's always optimal, right? So because it's always optimal, you can go, okay, how to put it? You can go from any, so although that we only constructed it from 0 to -1, -2, -3, -j, but if you want to go from any point here to any point here, you know, you go from this point to -j first, this point to, so let's say this is T2, T1. Then, you know, by our construction, you can just go from T2 to -j, -j to -j plus 1. Up to this point, so you just go in step. And from this step, you go to T1. So therefore, we always have uh, u of gamma t1 minus u of gamma t2 equals integral from t2 to t1 L of gamma dot ds plus c naught of t1 minus t2. Okay, so this one always implies that gamma is in ck of any such interval, and gamma satisfy the Euler-Lagrange equation. So hence, although the construction is piecewise, but when you patch things together, magically everything is smooth, everything is ck. Okay, so that's why it's really interesting. Thanks to all the tools that we have developed, uh, without them, we wouldn't be able to have such a smoothness, and we wouldn't be able to, uh, you know, to have such a conclusion. All right. So I'm going a bit fast today, but I want to just to give you a very big pictures of things, and now we have time for discussions or comments or anything of interest. Anything you would like to discuss? No. Come on, you guys are quiet, or maybe it's too easy or something. Again, I don't know. I mean, I'm how to put it. So I mean, when Fatihs and people in Wickham theory, like before Fatih, there was John Matter and the Brazilian schools of dynamics with brilliant people like Mane or others. They have been working on this. Um, um, and they have seen that this is not a perturbative regime. One cannot use the KM theory. KM theory stands for Kolmogorov-Arnold-Moser theory. That was a perturbative theory um, to do the result. And they see that, you have to really deal with the non-perturbative regime where H and L here are very general Hamiltonian or Lagrangian. And, people have to really, uh, just study the minimizing curves and connect the dots. So, this is it's a very important result for us to see that there is such a function u. It's so-called the Wickham theorem, or sometimes people say U is a Wickham solution. Uh, and it was done very naturally. For example, in the proof today I present to you is very, very uh, beautiful and very fundamental, right? We are using the smoothing effects and the fixed point theorem. What people were not aware of was that there were certain PD results in homogenization theory in the 80s that gives you exactly this kind of theorem for a much more general class of Hamiltonian. You can even do it for non-convex cases. Um, and recently, in the 2000 periods up to now, that people have been able to bridge the two communities between dynamical system and PDE together to see the same sort of like point. And um, I guess that by the end of our class, I will be able to give you the third proof by using PDE. It's much simpler. However, there's a weakness of PDE is that sometimes people only care about well-postness. They prove the result and they go away. They don't try to go really deep into understanding the deeper properties of calibrated curves. And that was the viewpoint in the 80s. But at this moment, then we are now trying to combine the tools and trying to use different viewpoints to get deeper to understanding about the dynamics. In particular, our main focus after today's lecture gonna be understanding about gamma. So that's sort of like a very important goal, right? So maybe let me just say it. So after today, so then we will investigate the properties of gamma, right? Uh, Again, I mean, from the theory we have proved so far, we only knew that it's CK satisfying Euler-Lagrange equation. We don't know about its behavior, right? For example, you can draw the torus out, you know, as this cubes. You can start at a point X here. A natural question that people can ask is that does it wrap around all the torus, or is it dense? Is orbit, is it dense in the torus, or is it what? Is it periodic in the torus, or what is rotation vectors and stuff like that, right? You know, a natural question would be a rotation vector. That do I have gamma s over s as s goes to infinity minus infinity converge to a vector? So those are the very basic questions that we're going to address, and I can say for sure that even those basic questions up to this moment, it's not very clear. um, you know, we have certain results, but and then sometimes if I cannot talk about the rotation vector, can I talk about the invariant measures, right? You know, its orbit is sort of like somewhere on the torus, then I can record its orbit in terms of an invariant measure, and then what can I tell about that? It turns out that if I do so, then I'll come with so-called invariant measure. It's gonna give you the Mather measure in honor of John Mather. He passed away, but he was at Princeton. You know, so here then we can start defining uh, basic aspects in dynamical system and go about to learn them and see the properties. However, of course, you know, there's still a lot to be done because once we relax the thing and we define invariant measures and do analysis with that, um, things start getting loose, you know, like it's not very easy to read up deep information out from that. So, you know, but I can tell you right away that, you know, rotation vectors in invariant measures can be defined very easily, right? You just you know, take the average of the orbits, and you know, in a nutshell, it's something like this. You know, you take say you take gamma, you just take the orbits from minus t to 0 first, and you're gonna record its orbits by you know, by, so you have its orbit is gamma s, gamma dot s, right? For s between minus t and 0. So this can be recorded as a measure, say mu t, I guess. So that you have, if you plug in any test function, c of gamma s, gamma dot s ds, what I'm writing, not, this is not correct. Minus t to 0 and taking the average. This one is being recorded as a measure, c of xv d mu t of xv. Okay, so the orbits, it's being recorded in terms of a measure, right? This is just, you know, essentially, you can say that, you know, in terms in the what, in the discrete terms, it just recording the frequency or whatever, right? So you record this orbit as a probability measure, in the phase space or something like that. And then in order to see the ergodicities or the large time limits, then again the orbit is not clear, but I have mu t is a sequence of probability measure. And remember that gamma dot is bounded, right? Gamma dot is bounded. That's thanks to our Euler-Lagrange theorem. So we have that the support of the measure mu t is always in the torus crossed with some big ball. Then you can pass the limit. You can let t goes to infinity. You can, by subsequential limits, you can see that mu tk gonna converge in quickly in terms of measure to some mu in mu bar probability measure with compact support. And this one turns out to be exactly the so-called matter measure. So that's the ergodicity of how we, like see the sort of like record the orbits, and we pass to infinity and defining invariant measures. It's very beautiful, very simple. We don't need a lot of deep dynamical system here. It's just, basic steps. Is it clear? Or, I mean, just the big picture, we're going to work on it. Any questions or concerns?
So we have these measures on Tn cross Rn for each. So for each T in the path, that's a measure, right? So is that creates a measure on the path gamma, or is this just a measure on the space?
Yes. So essentially, its support is just going to be on gamma, on the part gamma dot, right? Yeah, but the support is you can just say the support of mu t is on the whole space, but essentially it's just going to be concentrated on the part gamma dot.
Okay.
Yeah. But this is a very beautiful way from going from the orbits to measures. And then the key thing is that you know what I wrote down about rotation vector over there is that there are examples, not many, that we don't have rotation vectors. It can be really weird. The orbits can be weird in the torus, but if you take the measures, then the measures it's weaker. You know, it's in a weaker sense, and once you have it in a weaker sense, you can use compactness easily. So it's a kind of relaxation, right? Dealing with the parts is too rigid, and you lack compactness, but you relax it. So this relaxation idea is really beautiful. It occurs a lot in optimal transport in a lot of fields, that you relax it. You consider something weaker. In this case, we consider measures weaker, but we have compactness. And the support of mu, when t goes to infinity, then the support can be more complicated, right? For fixed time, then sure, it's only on the orbits of the gamma. Any other questions?
So is there a way to understand better about the limiting matter measure? If you want more information about it, is there any kind of tool or what people have developed?
No. No. So that's, again, you have been working on homogenizations and quantitative results. That's one of the key ways to understand the rotation vectors. Quantitative results about how fast gamma S over S converging to the rotation vector. A very simple question is that, can you quantify the speed of conversion of the measure mu tk to mu bar? I don't think anyone has ever done it. That's also something that I would like to do, honestly. Right? The problem with relaxation and with conversion that it is great, but it's just a compactness result. We like again, what do I mean by how fast the measure converges to the measure? It could be in Wasserstein distance or whatever. I'm up in the air about, but I'm sure that no one has ever done such a quantitative result, and that's, I believe that that's important and that should be done. Yeah, but no, we are, you guys are, this is lecture 25, so we are nearly 2/3 ways through, and we are now in the uncharted territory already. I'm going to tell you some results, and if you ask something further, then I don't know. but you know, yeah. So so let me put it this way: you can impose conditions, and can you by those imposed conditions can you get certain quantitative conversion, uh, or some better understanding about the behaviors? Then I would say no. But again, this is already a big deal. I mean, I mentioned all the big names, and people have been working on it really, really hard. Like from the dynamical system community, people like John Matter. There's a physicist called Aubrey in France, dealing with physics, but it turns out that it has relation to this, and it's so-called Aubrey matter theory and 2D. And Ricardo Manes and others in Brazil. After that, there's Albert Fati and the whole French and Italian school. In the PD community, then there are people like Craig Evans, Diego Gomez, Yi Feng Yu, and others that came into that. So it's really a big subject with having lots of different interpretations. And what I'm telling you here is exactly the same idea in optimal transport, which is a big deal, right? You do relaxation. Uh, yeah, but to date, up to this point, there are a lot of things to be done. I'm optimistic, but also cautiously optimistic because there's I don't know. Yeah. So anyhow, I hope that the whole picture is kind of clear. Um, yeah. So we're gonna switch to measures and defining invariant measures and stuff like that quite soon. Other concerns, questions?
I have a question. So if you scroll up a little bit,
Mhm.
so suppose I wanna find u minus iteratively.
Uh-huh.
So could I do a linearization of L, and then I minimize? I find from the minimization from the linearization of L, I can find a u and a gamma directly because it's a linear problem for a short time. And then can I repeat that over and over, and then let the linearization let the approximation go to 0? Then can I do it that way?
That's a good question as well. So honestly, on the top of my head, I don't know. What I can tell you is that this point of using the fixed point result is exactly in the same framework like the Italian school that they have been doing semi-Lagrangian approach. So the name that I can pinpoint to is this is a so-called the semi-Lagrangian approach. This is the whole Italian school. I you can search for the name. It's not good. Italian. Uh, um, Falcone, I guess, and some other names. They're really dealing with in order to solve the problem, they're really dealing with surely this kind of problem, right? They try to do the inf of ht of z or h1, or you can fix a time step. You can do h tau of zx plus uz plus c naught times tau. So what I can tell you is that yes, you can do certain linearization, but you have to be careful. And if I remember correctly, from the this semi-Lagrangian approach score, once they are doing such approximation, they also need to take into account the Euler-Lagrange equation. So they could solve the Euler-Lagrange or the Hamiltonian system for short time. right? Because that would correspond to the minimizer, and of course you can do linearization and stuff like that there. um, I don't know the complexity and how fast is this approach. It always seems very theoretical to me, honestly, because like you have to do lots of step in there, and like how do you uh, interpret that and code it? It's not very clear. But indeed, this is the big score, and I think they wrote a big book on that. You can search for I forgot the name. There are two authors, so Falcone and one more. They wrote a very big book on semi-Lagrangian approach in 2012 or something like that. Um, yeah, but indeed, this is one method. Um, yeah, but honestly, solving things either numerically or designing a correct ones to do it both theoretically and numerically is quite challenging. It's a complicated problem. Great. Any other concerns, questions? Okay, so it turns out that you see we discussed a lot today, starting with the two basic results, and you see that as we evolve, there are a lot of things that got to be understood better. And as you can see, any of your question here is already related to research problems. So I'm very happy to tell you about what I know and what I don't know. And right, so I can see you guys all back on Wednesday. Then I'll try to have the lecture notes done and post it in a timely manner for the next one. Okay, thank you all and see you later. Stay safe and healthy as usual.
Thank
Bye.
you.
Thank you.